Thank you to Maurice Pickles, who's agreed to pick up this last session of the day. Maurice is a ECMID AVI accredited vessel inspector. That's the scheme that our sister company, the Marine Surveying Academy, runs for IMCA. So very experienced at looking at offshore assets and auditing them and so on. And I think dynamic positioning is something that perhaps a lot of general surveyors don't know a great deal about. So when Maurice came along and said, I'd like to speak, I said, great, bring it on. So Maurice, without further ado, over to you.
Thank you very much, Mike. Okay, good afternoon, everyone. And if there's anybody watching, listening, who is familiar with DP, this might be a little bit on the basic side, but it is for the benefit of everyone, and definitely those who maybe have heard these two words and think it is akin to the Starship Enterprise. And is it the best thing since sliced bread, or is it toast? Let's see what you think when we get to the end of it. So dynamic positioning, what is it and what can go wrong? So I'm going to cover this really in 3 or 4 sections. What is it? And we're going to talk about what it is. I'm going to talk a little bit about the components of a DP system. I'm going to talk about vessel assurance for DP vessels, what typically a charterer, typically an oil major, would be looking at in order to allow a DP vessel on hire to enter into its restricted zone. And I'm going to finish off with a couple of the biggest dynamically positioned incidents that gripped the world globally, made the news globally, etc., including one that became a Netflix movie that some of you might have seen. So moving on, so dynamic positioning, what is it? So what am I going to try to do here? Just provide an overview. Benefits of being on DP, the difference between DP1, DP2 and DP3, industry best practice in relation to DP, and regulations around DP. So what is it? So it is a computer-controlled system to automatically maintain a vessel's position and heading. The system controls the vessel's propellers and thrusters based on information received from various sensors. And there on the right, you can see a kind of a general block diagram of the way of the inputs into the system. As I say, it's very much a computer, and the computer processes the information from sensors. They are absolutely imperative to the performance of the DP system and its reliability. Moving on. So what are we talking about here? We're talking about position reference systems, which can be satellite-based, i.e. GPS or GLONASS, radar-based sensors. There's a system called radar scan. Laser-based, which is fan beam. These systems operate, you basically would put a kind of reflector on board an offshore installation or another vessel, and you basically, you bounce a laser off it. And obviously taking into account the speed of return, etc., and the angle from the transmitter and receiver will give you a single position. Then moving on, we've got sonar based. We can put beacons on the seabed. They can either be transponders or responders, meaning that obviously a transponder, once it's pinged, it will actually transmit a message back to the vessel, and the responder is more passive. And then we've got the physical reference system. We've got something called a taut wire. Taut wire is probably one of the front runners, the older systems when DP vessels came out before the likes of GPS, etc. And this is basically a weighted line. Normally would have a very heavy concrete block on the end of a wire, which is deployed overboard, and basically once it's on the seabed, the vessel will go through a series of short trials and then basically hit the set button, and will monitor its position dependent on the angle and the length of the taut wire based from its datum position. So what do we need in a dynamic positioning system to be compliant with rules? Generally speaking, we need three position reference systems available at all times, of which 2 should be online and 1 should be functioning and on standby. Depending on the operation, some vessels may have more available, some may even have 3 systems online. If you want to look at just the basics to comply with the rules, then you are required for DP 2 and 3 to have a minimum of 3 systems available to you. So what are the benefits of DP? Well, operating alongside an installation in DP is generally considered safer for the following reason. Station keeping is fully automated and therefore more accurate. DP is typically less susceptible to human error caused by fatigue, distraction, boredom, limitations of experience, natural ability and skill. I'm going to challenge that later on. And equipment redundancy and configuration lessens the likelihood of a loss of position due to technical failure or blackout. So in the I'm assuming that, well, I won't assume. The term redundancy basically means, in case anybody does need clarity, if you've only got 1 engine, you have no redundancy. If you've got 2 engines, but you're operating on 1, you always know that if that engine breaks down, you can bring another engine online. And in the case of dynamic positioning, this would be automated such that in the event that the power demand had got to a certain level, the system would automatically start additional power plant in order to make sure that the vessel could maintain position or heading depending on what is required. That's redundancy in a very, very simple, that's explaining it simply. So what about dynamic positioning DP classes? So here we've basically got, actually there's a lot more classes these days, but there used to be DP 1, 2 and 3. Now we've got DP 0 and we've got DP 3, we've got enhanced DP, we've got all sorts of class notations, you know, enhanced redundancy, classes based on the type of maintenance and reliability that goes into them. But for the purpose of this, we'll try to keep it simple with the 3 most common DP classes. So DP1, as it says there, vessel position is maintained automatically. So it has a system on board, it has a computer on board, it may actually have 2 engines, 2 thrusters, it might have all of this stuff. So in theory, it has redundancy, but it's not automated. So what it says there is loss of position may occur after a single point failure, i.e. an engine, thruster, sensor or other component failure. And the little diagram to the right, basically what that's trying to mimic is you've got a computer screen, you've got 2 bow thrusters, 2 stern thrusters, 2 propellers, and that's basically it. If anything goes down, there's nothing to, as an example, if the computer fails in that system, then the system is basically US. DP 2 or 3. So in the case of DP 2 or 3, vessel's position is maintained automatically and will not lose position after a single point failure. Just to go a little bit further on that, that is generally speaking, there's static components in the system that if they fail, there should be no loss of position. And in the diagram on the right, you will see there are two computer systems, red and blue, just for simplicity. So what that's basically depicting is if your red computer goes down, then the blue computer can pick up the reins and can control the vessel, meaning that a loss of position should not occur, and therefore a risk of a collision with an installation or whatever is reduced. Just a little bit about DP3. DP3 has exactly the same redundancy concept. The main difference with DP3 is that she has additional damage control built into the design of the vessel, excuse me, that will restrict, that will minimize that. Sorry, what am I trying to say? It has additional damage control built in, such that if there was a fire or a breach of water integrity, that can be controlled. A simple way of thinking of a DP3 vessel is that it is actually two ships of the same type, joined together and separated right down the middle by an A60 type bulkhead. And if one side of the vessel is damaged by fire or flood, then that vessel can maintain position, or at least keep it, or at least get it to a position of safety, with one half of the vessel still operating exactly as per design. Dynamic positioning best practice. So, I mean, obviously, dynamic positioning came about in the 70s with very crude systems. Probably most of them would be DP1. And yes, they were basically computerized systems. Some of them would have been operated simply by using a joystick on the aft bridge of a, say, for example, a platform supply vessel or a diving support ship. And slowly these companies like Kongsberg made them much more complex, which has resulted in the systems the very reliable systems that we have today. Also, DP has it's spread throughout the maritime industry. We've now got DP on tankers, shuttle tankers, for example. We've got DP on cruise ships that may go into, say, an area where they can't go alongside, and they don't want to drop anchor to disturb the environment of the seabed, as an example. So they will typically go on DP and then launch their launches to take people ashore. Even small offshore crew vessels these days in the Gulf of Mexico have got DP systems on them for maintaining positions alongside installations. Again, DP1 is normally restricted to open water, low risk activities. Typically, DP1 would be used on say, a seismic vessel, for example. And, you know, some older PSVs would still have a DP1 system. But generally, as I say, these would be used in open water or in downwind type situations where if they did lose a position, they would actually blow or drift off the location. Not many operators would let them work upwind of an offshore installation with a DP1 system. I guess I've just covered that in the next bullet. And then minimum DP2 required where is a risk to human life or the environment. Depending where in the world you work, some places have additional rules. Norway, for example, they've got something called NORSOC guidance on the DP classifications for different operations. So, for example, diving operations, I think they require a minimum DP3. Drill rig operations, DP3. Well intervention, DP3. And then you have lesser DP classes for pipe laying, cable laying, platform supply vessels, etc. But the bottom line is that whenever you're planning an operation with a DP vessel, it should be subject to a risk assessment so that you do get the right vessel for the intended industrial mission. So when it comes to the vessel and associated systems, they must be properly commissioned. We've got this thing called an FMEA, a failure modes and effects analysis. If anybody doesn't know what that is, FMEAs originally came from the aviation industry, where I think it was probably Boeing that invented them, basically to go through a series of tests that say, well, if it can go wrong, what will happen if it does go wrong? And then they get a table of expected results and make sure that the aircraft can still fly. And if it can't, then they need to find a way to fix that. So basically, DP vessels follow a very, very similar protocol in that regard. They are designed, FMEAs tend to be theoretical documents. They are desktop documents that then go, once they're finalized, vessels go out and prove the FMEA to make sure that it works exactly as it should, that if anything breaks down, that the results are as expected, and that people know what they need to do to get themselves out of trouble, etc. And what an FMEA also does is come out with something called a worst case failure or a worst case design intent. That also needs to be proven so that everybody knows if a certain piece of equipment goes down, they may use a bow thruster, a stern thruster, a rudder or whatever, and that is going to be their most serious position. So as I say, after the FMEA, we go to FMEA proving trials. We also have DP operations manuals, and we have things called critical activity modes of operations documents, activity specific documents. These are all made depending on the nature of the operation of the vessel and to help with decision-making processes in the event of any kind of failure. In actual fact, the failure should never occur. It's about incidents that happen before a failure and decisions that should be made to prevent that failure from occurring. DP trials and FMEA, well, you've got annual DP trials should take place every 12 months with a 3 months grace period either way. And FMEAs should be proven at least every 5 years to prove that everything works as it should. And generally speaking, the charterer should assure themselves that the vessel is always compliant by auditing and inspecting the above. So dynamic positioning, regulations and guidance. We've got our friends at the IMO have got guidance on DP design, etc. This for a long time was out in a document which was known as IMO 645. This was recently revamped because 645 was a little bit lacking, really. It was about 20 years old, and the advancement in the design and operation of DP vessels had moved on so much. So there's now a new set of guidance. I think it's called, is it 1583, that applies to vessels that were built after a certain date, which I can't remember off the top of my head. We've got classification society rules. Obviously, any IACS classification society should have a robust set of rules that cover DP. They're all similar, but neither two are exactly the same. But in general, they do follow the fundamentals of the redundancy and the equipment classifications, etc. There are two main bodies that issue guidance for the operation, DP operations, and those are the International Marine Contractors Association. They've been doing it for years. They kind of took over from the DP Vessel Operators Association a few years ago, and they've been superb in circulating industry guidance through the whole of the offshore industry and beyond for good and best practices in DP operations. They also have a DP incident reporting scheme, which is an excellent thing. It is basically, it's anonymous when it goes out to the public, and it's a good way to promulgate information about DP incidents and lessons learned. Second, not necessarily second in second best, but the other one is the Marine Technological Society. This is an organization based in Houston, Texas. And these guys are much newer, much more recent than IMCA. And if I dare say, in my humble opinion, they are a little bit more technical with the guidance that they produce. But thankfully, they do, in most of their guidance, they do refer to the IMCA guidance, which is great from the point of view that we don't have conflict in, which guidance are we operating to? So that's a positive thing. And there we've got the bottom bullet. Duty holders normally expect all DP vessels on hire to adhere to flag state, class, and IMCA or MTS requirements. So just talking about DP vessel assurance as an example, we've got typical questions that would be asked by an attending surveyor would be, you know, what's the date of the most recent FMEA? And as I've already touched base on, these should be within 5 years and should be, so you've got the actual FMEA document itself and the FMEA proving trials, and these should be dated within 5 years. FMEA proving trials, I don't want to get too deep in this. It is meant to be just kind of scratching the surface. But what you can do is split all of your 5-year trials, all of the trials you would be expected to conduct over 5 years. What some companies do is split them up so that you actually do 20% of them each year. So that within a 5-year period, you will have conducted every trial that was expected in the FMEA. And that's perfectly acceptable. In the case of where FMEAs are out of date or out of 5 years, then it is up to the oil major or the charterer to decide whether or not they consider that the vessel is suitable to hire or not. Some may insist the vessel has a proving trial before they will take it on hire. Some may actually commission their own trials, but that's very subjective. Next, we talk about annual DP trials. These, in a lot of cases, they are very, very similar and contain a lot of the tests that are in the FMEA. Typically, a vessel would leave a supply-based port or come out of dry dock, go out to a place out of the way of a shipping lane, etc., a sensible water depth, and would basically go through a set of trials using the DP system. Might put beacons on the seabed, might just use GPS, just use whatever it can and just prove that everything works as it actually can, as it's designed to do. The whole principle of these annual DP trials is that they should be independently witnessed, meaning that somebody should be on board that doesn't represent an oil company, doesn't represent the vessel owner, the operator, doesn't represent Kongsberg, class, flag state, but is sufficiently knowledgeable to go and just observe the trials and make a report just to say that everything worked exactly as it should. Again, if a vessel is out of date for annual DP trials, this could lead to problems for the vessel being chartered. And again, it would depend on I'm guessing, charterers' requirements, market conditions, etc., whether or not a vessel would be hired on that basis. Okay, this one, don't get daunted by this drawing on the right side. One of the biggest things in DP, and an argument that goes on forever and ever and ever without any, it is subjective, is about bus ties. So basically, how can I explain this in a simple, if you imagine you've got two switchboards and a bus tie sitting in between, or a series of bus ties in between each switchboard, what you need to find out is, if you had a fault on one side of that board, can that fault transfer across into the other side and then completely black out the vessel? So what we tend to work in most cases is we talk about open and closed bus ties. Now, open in a lot of people's minds, tends to conjure up an image of a good thing, and closed conjures up an image of a bad thing. In the case of DP and bus ties, most operators would want you to operate with an open bus tie, meaning that it is not connected across the board. Meaning that if you get a fault one side of the board, the fault stays there, and the other side, all of the machinery, all of the switchboard, everything the other side of that is still capable of working, and the fault is kept on the side of board that it originated. If you close those bus ties, then as I said previously, there is a risk that the fault can transfer across, and you will end up with a complete blackout of the vessel. So we've had over the years many arguments about this. We've got we've got companies that have really invested millions in trying to develop the perfect bus tie and circuit breakers that are fault tolerant, that will not allow faults to transfer, or that will immediately open in the event of detecting a fault. But I don't think anything has been perfectly designed yet that can prevent a fault transfer. So a lot of, when you look at an FMEA, for example, one of the first things to look for is the design of the vessel. Is it designed to operate with an open or closed bus tie? And if so, has it been tested against those conditions? And again, it's still very, very subjective, that there may be, the operators may still refuse to allow vessels to operate with a closed bus tie whilst inside their restricted zones. Another important thing here, I know earlier on there was a statement about the human interface and a lack of opportunity for problems caused by people. In actual fact, that has been proven to be wrong. And one of the biggest factors with dynamic positioning and DPOs is the fact that DPOs, a lot of them are very, very good at operating a DP system, but they rarely handle a vessel in manual mode. And it is a skill that's either quickly lost or in some cases never developed. So in the event of a DP system catastrophic failure, and they need to drive the vessel in manual, it has left a lot of people kind of, they're like a rabbit in the headlights. And I know a lot of the DP training establishments are currently looking at this. Activity operational planning, I just touched on this earlier. Again, I'm not gonna go death by PowerPoint with this, but we've got two or three things to think about here. We've got the critical activity mode of operation. We've got the activity specific operational guidelines, which exactly as it said, activity, what am I going to be doing and where am I going to be operating, and examine it all exactly as per that. And then we've got task appropriate mode, which is risk based. That in actual fact, task appropriate can, depending on the nature of the operation, can mean that the vessel can be operated outside of its usual operating limits. So that one needs to be well and truly documented, and obviously all risks mitigated before that can take place. So with so much technology, training, redundancy, procedures and insurance, what could possibly go wrong? Well, if anything can go wrong, it will, as we all know, Murphy's Law. So let's have a look. Let's have a look at what can go wrong. So look, those two pictures there, from this to this. So what did we have? We had a vessel alongside an installation offshore India, of which the cook cut his finger, but it wouldn't stop bleeding. So it was thought that he needed to get medical attention. So the vessel was called the Samudra Suraksha. Conditions were, she was at the Mumbai high location offshore India. Rough seas, 20 to 25 knot winds, 2 knot currents, and a 4 to 5 meter swell. They're pretty much marginal conditions for any DP operations. I think 4 to 5 meter swell these days, I'm not entirely convinced that DP vessels would continue to operate in that. So a little bit more about the vessel. She was built in 1982, DNV, supply vessel code. She was DNV class 2, etc., etc. Quite a large vessel, 102 meters long, 19.5 wide. The Mumbai High complex is 160 miles west of Mumbai, and there you can see the details of it. 384 persons were on board in the whole complex, including the drilling rig and MSV. So what initiated the event? As I said before, cook was injured, cut finger. Weather wasn't suitable for helicopter operations, but the master and OIM agreed on a basket transfer. Basically, just as it says there, this would be a transfer basket onto a crane, and the person would hold on and would be lifted off the deck of the vessel and transferred onto probably the heli deck of the offshore installation. The master elects to maneuver the vessel using joystick DP. He experienced some problems with an azimuth thruster, and then he decided to operate the thrusters in emergency mode. So he basically bypassed the DP system. He tried to move the vessel away from the platform, but it was unresponsive. Next thing was it scraped against the platform and made heavy contact with the risers. Just in case you aren't aware, the risers are basically all of the product carrying pipes or gas carrying pipes that come from the seabed up into the offshore installation, and the vessel then remained out of control at about 16:05. Hit the platform, huge gas leak, and fire broke out. Flames engulfed the bridge of the vessel, and burning debris was basically spread all over the ship. Then there was a load more explosions took place, distress messages sent, and as you can see, it became a major emergency offshore India. 15 offshore supply vessels and multi-purpose support vessels responded to the incident. 22 lives lost. And there's a picture of clearly unbelievable, just unbelievable from a cut finger. Root causes that came out of the incident, I'm sure there were a lot more, but these were summarized in a report that you can actually download online. Adverse weather conditions, a weather side approach. I touched on that briefly before. You know, weather side. If you're weather side and anything goes wrong, you can't unless everything's working properly. You're gonna get blown on, or you're gonna be drifted onto the installation. Absence of procedures for vessel platform interface. Absence of interaction between an inexperienced OIM on the Mumbai and an overconfident master of the vessel. And operating alongside the platform with unprotected risers. On that final point there, because this is about DP, I didn't go into any detail about this, but another thing, one of the major things that came out of this incident was the importance of riser protection that was built to design a particular vessel size at an impact of a particular speed. So this is something now that's built into all offshore platforms worldwide that came out of this incident. Root cause continued, maneuvering misjudgment or operating error with possible machinery failure. DP control would have allowed for the appropriate thruster output, but you know, he basically overruled the DP system by going into manual. And there, that picture to the right is what was left of that platform. So that was that particular incident. That was the Mumbai High. And as I say, you can research quite a lot of information on that on the internet if you want. So the second and final incident I want to talk about today and bring my presentation to an end. If anybody has seen this, there is a film on Netflix at the moment called Last Breath. And this is actually factually correct. Yes, it's got actors in it, but it also has a lot of footage that from the actual incident itself, and includes interviews with the people that were involved. It's actually pretty incredible. So the vessel was a Bibby Topaz, a fairly modern offshore support vessel built in Norway, DP Class 2 diving support vessel. She was working over a subsea template, and then there was a DP Amber Alert. DP Amber Alert, that's basically, if you imagine UK traffic lights, amber means caution. With an Amber Alert, there will be procedures that maybe the divers would stop what they're doing and return to the bell, or they would stop what they were doing and await further instructions. But there would definitely be procedures that would say what to do in the event of an Amber Alert. So they had this Amber Alert. The vessel starts to drift. The dive control was informed. So there you go. Diver supervisor instructed divers to leave the structure and locate the bell stage. And on the bridge, attempts were made to reselect the thrusters into the DP system. At 22:11, DP Red Alert activated. So that basically means we've now got serious problems. We no longer have control of the vessel, and we're now drifting. As you can see, the vessel had started to drift to the east. The master switched from DP to manual thruster control and tried to maintain position in manual. And the divers were still located on top of the template. Please remember, only 2 minutes had passed between the Amber Alert and the Red Alert in this particular case. What happened, one of the divers, unfortunately diver 2, his umbilical snagged on the transponder, and diver 1 was pulled off the template by his umbilical and everything. So as the vessel drifted, he was basically just getting towed by his connection to the bell. The other guy was trapped on board the subsea template. And his umbilical actually parted, leaving him with his basically personal survival kit. He would have had no heating or anything like that. Basically, the heating in these kits comes from hot water that's circulated around the diving suits, that's pumped from the vessel via the bell into the suit and round. He would have lost all of that. So he would have been getting cold very, very quickly. Ultimately, the vessel then drifted in 5 minutes, drifted 240 meters to the east of the template. That's a good distance away, 240 meters. During this time, they were still trying to recover control of the vessel. You can see he had diver 1 eventually made his way back to the, with the assistance of the diving supervisor and the guy, his buddy in the bell. He managed to get himself back to the diving bell. So he was safe. At 22:40, so again, a good time later, the vessel had managed to maneuver itself back over the top of the template, and diver 1 went out again. He actually went against orders, if I remember correctly. He went out to go and save his, to try to recover his mate. His diver 2 by this point was unconscious. He was in early stages of hypothermia. He was in a bad way, and his reserve air was very, very low. They managed to get him to the bell around about 22:46. He was unconscious but still breathing. And at 11:05, they established he came round, his vital signs were good, and he was talking. And then they sealed the bell, took it back up to the vessel, recovered the ROV, and just before midnight, They basically done an emergency run to port to get the to get medical treatment for the diver, etc., and also to find out what it was that had gone wrong with the DP system. So, I mean, I've got some technical. There's some technical stuff written here about what the causal factors were, but basically, in a nutshell, this was regarded as what they call network jamming, and it basically was. It's like an electronic storm that hit the DP system and made all of the data unreadable by the computer. And it basically meant that everything dropped out. The vessel started drifting, and it didn't matter what they did, they could not get control of the vessel. They basically had to restart the whole thing. They had to basically switch it off and restart it, which took, I believe, about 7 minutes. And that was the length of time that it took for the vessel drifted 240 meters. This did result, the DP manufacturer was Kongsberg Maritime in Norway. And Kongsberg did this, they managed to fix the problem, and they issued an industry safety notice about an upgrade, a patch upgrade that was needed in order to make sure that this couldn't happen again. So lessons learned from that. Again, these are just summary. There was a lot more, but these are the summary ones. The incident produced much interest for many vessel operator and diving contractors who launched a campaign for safety enhancement of diving and marine operations. There was an enhanced DP control system design, inspection and verification regime. DP field entry trials and set up to enable time for driving the vessel in manual mode. Very important. And an enhancement of the understanding and familiarity of manual systems and operation. Other things that came to the surface were bridge team management. The fact that the DP system upgrades, etc., all had to be integrated into the FMEA and available for review, and a competency scheme performance criteria for trainings, drills, and exercises. So this is my last slide. Just some simple takeaways from what we've spoke about in this presentation. Competence, always a factor, especially in the consequence. Company procedures, we all need good, robust company procedures, and we need people who are prepared to work to these procedures. Maintenance, maintenance records, challenge when maintenance hasn't been done in line with the schedule. Good old-fashioned seamanship. DP operators must know how to handle a vessel in manual. It's absolutely imperative that we get this aspect of training into DP operators training. The resistance is caused simply because it is impossible. Whilst the DP system can be very generic, where the layout of a bridge could be, you know, there's probably 1,000 different bridge layouts around the world, and the ergonomics of them are they're not the same. So it's difficult to try to train people for that. Importance of information sharing, DP incident reporting. It has a positive effect to alert other operators to consider their own procedures. So that, my friends who are still here, that's the end of my presentation. I hope it wasn't too much to take in. But if there's any questions, I would be very pleased to see if I can answer them. Otherwise, that's it from me.
Maurice, thank you very much indeed. Very comprehensive, really interesting. Any questions anybody wants to raise?